Right, so hello everyone, hope you can hear me. Never sure with these things. Okay, someone could just say yes, you can hear me on the chat, that'll be great. Otherwise I end up talking to myself. Good, excellent, thank you. Right, so at the end of the last session we started looking at example. I'll just go back a bit on the slides. So we were looking at an example of some signal conditioning based on some research that we did a few years ago. And so we were trying to come up with sensors that would fit in the ground. Let me just get rid of me now. And we wanted to look at the signal processing, the simple signal processing, or the simplest we can get away with really, to be able to analyze that signal. But to do that we had to understand the sensor and what kind of signal it was generating. And in this case we had a potentiometric sensor, which means it generates a voltage. So we wanted to be able to fundamentally measure a generated voltage, but we had a slight complexity in it being a chemical sensor, that it was only generating a voltage with respect to some chemical potential. So we had to create a reference potential to measure against. So if you thought we were measuring, say, half a battery, we needed the other half cell, and we made use of this chemical reaction between silver and chloride and silver chloride. So there was this sort of reversible reaction between silver chloride and silver chloride, and we were interested in the chloride in the environment, which is down here, and as this concentration changes, which is what we're interested in, this whole sort of equation that relates to the balance of the equation changes, and E, the voltage out, changes. So change this one, we end up with a voltage change going on over here, and that's sort of what we're looking for. And this boils down to 59 millivolts change in potential for a decade changing chloride, which is, that's the fundamentals. We just have to work with that. And we made the sensor by screen printing, and I went a little bit about the screen printing process, how to make these things, how to make it robust and relatively cheap, and how we had to then create this reference electrode to measure against, because this is just generating a potential which changes with the chloride concentration, but we don't know what it changes with respect to. So we had to create another chemical potential, which was the same type of electrode, but put into a known concentration of chloride, and then we can measure the difference between this known concentration and this varying one that we're interested in, and we could work out the difference. So as long as we know what this concentration is, we would then know what this concentration is by measuring the difference in the voltage. In other words, if the voltage between these two is the same, then the concentration of chloride measured here is the same as the concentration of chloride in our reference electrode, and as this varies, this voltage difference will change. And so there was a bit of a discussion about how to make a reference electrode, which turns out to be quite a tricky thing to do. We had to invent this porous glass to achieve that, but we could make this sensor cell that we could then use. And they work really nicely, and they have a logarithmic relationship, as we expected, against chloride concentration in milligrams per litre. And we said that tap water is somewhere around about 6, 7, 8, depending on which part of the country you're in. And then plants tend to fall over and die in this kind of region here. So we've got quite a good range that's useful to operate within. So that's all good. So this allows us, that graph allows us to try and figure out the sort of voltages that we're going to need to be interested in to measure in our system. And we can see, let's just go back to the graph, that maybe, this is 60 millivolts. If we go down here, this is about 0, say, and this will be about 300. So if we said that our maximum range will be somewhere between 0 and 300, that's the range we're interested in, that'll be a good place for our measuring system to operate. So we start to get an idea of the design performance that we're going to need, at least for the input voltage coming in. It's going to be somewhere between 0 and 300, and most likely it's going to be somewhere between 220 or so and 120, so there's a range of about 100 millivolts. But chemical sensors are notorious for moving around a bit, so it's good to have a little bit of extra range within the system. So if we got a 0 to 300 millivolt signal that we're interested in, we want to put this into an A to D converter, and that operates at about 3.3 volts, then we can apply a gain of 10 to that signal. And so 300 millivolts times 10 will be 3 volts or so. So that's roughly where we go. So we're looking for a gain of 10, which isn't huge, which is good, so it's not unreasonable. And so we were sort of thinking in our minds that a differential amplifier with a differential gain of up to about 10 is a good thing, just to get this up to speed. And then there's some various issues with noise and stuff we won't worry about too much at the moment. And the other thing is we have to think about the signal we're trying to measure. So we're looking for a very slow moving signal, because the concentration of chloride in the ground in this case, we're not expecting it to change very much over time. It's not going to change by the second. It might change by the day, possibly by the week. It might change if it rains, that kind of thing. So we're not looking for a very fast moving signal, so our filtering doesn't need to be too onerous. It's a slow moving signal. There's likely to be noise on it, and let's assume that noise is going to be Gaussian, and it's going to be coming in both wires picked up from around in the environment. So it could well be that the noise is a common mode signal, and the signal we can make a differential mode signal. And because the noise is Gaussian as well, we can maybe average this signal, and this is where we sort of got to in the last lecture. We might want to just take a reading, say once an hour, of the chloride concentration. But if we just turned on our A to D converter and took one measurement and then went back to sleep again, that sensor reading will be the reading, and there'll be some kind of noise on it, and that noise may well be random, and it might be quite large. So we've got some uncertainty introduced into our creaking chair, into our system. But what we can do, because it's a slow moving signal, we can actually take lots of measurements, one after the other, just bang, 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 take a measurement. And we would assume that the chloride signal hasn't changed very much between those measurements. But the noise, being a Gaussian, may well go up and down. But the average of Gaussian is 0. So if we average those numbers, we would expect the noise to drop to 0 and get the signal. So we can, every hour we can wake up and we can take 10 readings one after the other, bang, 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 and then just average those readings, and that should improve our signal to noise. And in actual fact it improves it by root n, where n is the number of samples we've taken. So that's a good thing to do. And there's a slide here that sort of introduces this, showing that if we add up all our signals, so we're trying to get the mean over standard deviation effectively. So if we add up lots of our signals, so this is our bang bang bang, lots of signals, add them all up, and this gives us effectively our signal voltage. We can then add up the noise variances squared, and this gives us effectively our noise power. And we need to take, for power, we need to take the square root to get back to our noise voltage, so we can compare it with the signal voltage. And then if we do the signal to noise, then at that point we can see that we've improved everything by root n. And Ruomeng will be talking more about noise later on, but this is, intuitively you can see that if you add up lots of things that have a random distribution, the average should come to 0, and so that should leave you with your signal that you're interested in. So just to put that into some kind of illustration, there's a very simple processing technique that can apply in such cases where the noise is very fast and the signal is very, very slow, called ensemble averaging, or boxcar averaging sometimes it's called. So here's a noisy signal, and we can see there's a lot of noise, but we can sort of maybe see the trend in the signal. But it is a very noisy signal. So this is when you just wake up, take a reading, take it as gospel, go to sleep. An hour later or so, wake up, take the reading, go to sleep again. If you then start to wake up, take lots of readings at the same time, and average that, with 10 you can start to see that we're getting a much smoother picture in the signal. The noise is being reduced. There's still noise there, but it's average, if you like, the average of the noise has been reduced. If you take 20, it starts to improve even more. 50, very nice, starting to see the signal in this noise. 100, it's starting to get there, and if you keep going, it just improves matters. And if you could take 1,000 samples, then you're starting to see a very smooth plot in the data coming through, and we got rid of the noise. So this is a sort of a simple example of effectively digital filtering in action, because we have to store all these values up and add them together and then divide by the number of samples we first, square root of the number of samples we first thought of. So this does rely on the point that you're taking here, having taken 1,000 measurements at this point very quickly, one after the other. So the actual data points that you're interested in are quite widely spaced apart. Otherwise we have to be a bit clever about our signal processing. But in this case we can do that. So you have to remember there are some limits here. As I've just mentioned, then the repetitive measurement of the same sample is required. So we're assuming that the time that you're measuring this thing, that the signal hasn't changed very much, and it's really what's saying in this third point here. Signal has to be slow moving with respect to the sample rate. It does increase the time of your measurement by how many samples you're taking, because you've got to take those measurements, which could increase the power of your system, because you've got to take lots of measurements. It's got to be on for a bit longer. Maybe a problem. And the noise has to be fast moving with respect to your signal, and it must have an average of 0. So Gaussian, but most noise is that way. So it's a very easy way of getting improvements for slow moving, infrequently measured signals, which is the sort of thing you want in the environment. So you can see that with a bit of knowledge of the thing you're trying to measure, an understanding of your sensor, and some basic signal processing ideas, you can start to build the bare bones of a system that might actually do the job you're interested in. But then we get a choice of, well, what kind of amplifier are we going to use? We've said we wanted a gain of 10 or so, and we said it was probably a differential signal that we're interested in. How do we do that? So we can obviously build one from op amps, as we've looked at. We've looked at differential amplifiers with a single op amp. We've looked at differential amplifiers with 3 op amps, the so-called instrumentation amplifier. And we sort of hinted along there that if you want a really good one, you have to buy an integrated one. So here is a choice for our a naive choice for our instrumentation, or our instrumentation amplifier. It's called an AD623 from a company called Analog Devices, and the clue for that is in the name here, AD, Analog Devices. And its headline is single supply rail-to-rail low-cost instrumentation amplifier. So this is the first page of its data sheet. So it's worth understanding data sheets in some detail, as we'll find out. So on the face of this, it looks like a good system. Its first feature is that it's easy to use. So that all sounds good. Everyone likes easy to use. High performance and a discrete design. Well, that's not unexpected, so that's great. Single supply and dual supply operation. So on our recap of the limits of op amps, hopefully we can start to understand that this is actually quite a valuable feature. The single supply feature is quite useful. That says it should, if you operate it on a 0 to, I don't know, say 5 volt supply, it will operate down to the 0 supply, so the negative supply rail. And also it's like a normal op amp as well. It'll operate on dual supply, which as well if you wanted to, but they all do, so that's not much of a feature. Then it says, well, and we've got a rail-to-rail output swing as well, which means that the output can move from whatever the negative supply rail is to the positive supply rail. So we've got a good range of operation, and we talked about that as well last week as well. Now this is interesting. The input voltage range extends 150 millivolts below ground on a single supply, which means that you can actually input negative signals into it when it's operating on a 0 to 5 volt supply, allegedly. And this sounds like magic, but that just goes to show, I think, really, that if you've got signals that are equivalent of 0 going into it, you've got a chance of amplifying them. It's low power, and it qualifies that with 550 microamps maximum supply current, so it will take 550 microamps for each amplifier. In this case there's only one amplifier in the pack, so that's good. Low power, 550 microamps is reasonably low. It's not fantastically low though. Gain set with one external resistor, as you'd expect from an instrumentation amplifier. and it's all very accurate. It gives us some information about offset voltages, 100 microvolts maximum input offset voltage, and also 25 nanoamps maximum input bias currents. So and these are all features that we are familiar with now from at least last week and probably a couple of years before. And then it gives us some information about common mode rejection ratio for a gain of 10, and it varies with gain, and look, it's not quite as good as gain equals 1, it's only got 70 dBs, but it's not bad though, but only at 60 Hertz. But 60 Hertz is worthwhile because 60 Hertz is power frequency supply, so the mains voltage comes in at 50 and 60 Hertz depending if you're in America or in this country. So this is why it's quoted at that figure, because that's where common mode noise really is in these systems. And it's got an 800 kilohertz bandwidth, so it's not going to be looking at super fast signals, but for use in the ground where it's changing by the day, that's really not a problem. And if we turn it on and off, it takes 20 microseconds to settle down before you can start to take readings. So we have to bear that in mind when designing systems as well. So there's lots of stuff here, and then there's some words about it. So it's all wonderful. Is there anything else worth mentioning at the moment? So on the face of it, looks like good choice, instrumentation, amplifier, low power, rail to rail, no surprises, good performance. They're quite expensive though, a few pounds each. Right, so in summary then, looks good as it's rail to rail, operates on 3 volts, which is probably what we want. It's low power and its gain is set by a single resistor, so it looks like it's foolproof in many ways. It's expensive, and for our system we might want to have multiple sensors in our system to measure at different points in the ground, maybe 7 or 8, and we can't really afford to have 7 or 8 amplifiers, so we would like to, and the signal's moving really slowly as well, so we might as well have one amplifier and just switch the input to it from each of the sensors on a regular basis. So we also need to think about having an analog multiplexer. So a multiplexer allows us to switch many individual signals to one output point, so we can multiplex the amplifier, only use one amplifier and still get 8 signals coming in. And we still need to worry about references at the moment, and so we talked a little bit about references, and we need to get the chemical reference and the electronic reference, ground in electronics, to be at least related and ideally the same. And in this case it's easy, we just tie the ground of the electrical circuit to the reference potential, which is easy enough to do, but there is a problem in our system. So we've looked in some detail at the first page of the datasheet. Buried on page 10 of the datasheet, so it's a big datasheet, is this interesting diagram which we overlooked the first time round when we first designed the circuit. So it's a diagram linking maximum output voltage to the common mode input, and you just look at that and you go, oh, well, I don't quite really understand what's going on here, but it's worth just thinking about this for a little bit. These areas here are operating areas, so under these conditions Vs equals plus or minus 2.5. This is the inside of this sort of shape is where this thing can operate sensibly, and if you ran it on plus or minus 5 volts it operates in this bigger shape. But what does this shape mean? So the axis is labelled common mode input voltage, and this axis is labelled maximum output voltage. So this is how much output voltage you're allowed to have for a common mode input voltage. So we have to sort of think about that. First of all, we need to decide, well, where are we operating in this system? So Vs equals plus or minus 2.5 volts. So Vs is the power supply voltage, so this is operating on plus or minus 2.5 volts, which is effectively a 5 volt difference. So we might as well put our 0 at minus 2.5, and then we would say that we're actually operating on a 0 to 5 volt supply. So this is equivalent of operating on a 0 to 5 volt supply, as it says here. So if the common mode input voltage is 0 volts or no difference, then we're operating in this kind of range here. So if the signal is on a common mode signal that is very close to the supply rail, then we're operating in this point here. And what that means is that the maximum output voltage that's allowed is actually very, very small. So what we really want to be operating is a common mode input at around about here somewhere, which would be and our supply about 2 volts, so it's -1 from the middle of 5, so it's 1.5 volts or so. And then our output swing goes all the way to plus or minus 2.5 volts or 5 volts if we're operating on a single supply, so we get full range. If we operate near the supply voltage, then the output swing is very small, and likewise here, if we're operating close to the positive supply, the output swing that's allowed is really, really low, so it means you can't get much output out. So as it says here, this seems to imply that the maximum output voltage is very limited if we're going to be operating anywhere near the supply voltages on this slope here. And this was actually the case, and in our instrumentation system, the signals coming in were 0 to 200, 300 millivolts or so, which are actually quite close to the supply voltage, which meant that we couldn't really get very much gain out of this. Well, we could use the gain, but we can't get much actual output, which led to a lot of distortion. So it was a bit of a mess up on our respect, really. So we couldn't use this diff amp, so we had to just swap it for a normal non-inverting op amp which didn't have these limitations, which is a bit sad, really. All that design effort for nothing, and we had to just throw in an op amp. Actually worked okay in the end, so that was alright. So this is an example of a little knowledge is a good thing, but it's quite dangerous as well. A lot more knowledge would have allowed us to design a better circuit, or a more professional circuit anyway. And that's just the dangers of common mode voltage issues with differential amplifiers. Anyway, what about our multiplexer? So again, we have to look for all the features we're interested in. So this is an analog multiplexer, so in this case the ADG608, up to 8 inputs coming in, and we select each of these inputs can be sent to the output by selecting one of these switches, and it's set digitally. VSS to VDD, analog signal range, that means it's rail to rail in terms of the signal coming through. Can operate on a wide range of power supplies. Low on resistance, 30 ohms maximum, so when this switch is closed there's only 30 ohms resistance appearing in this route. Doesn't take very long to switch on and off, and it's low power, 1.5 microwatts. So the remember the differential amplifier we just looked at, that was 1.5 milliwatts, and they claim that was low power. This one is 1.5 microwatts, and they're claiming that's low power, and this is getting closer to being low power. So it's just a fairly standard sort of multiplexer, really, and it would be fine for our requirements because it's rail to rail and operates on low voltage. And we still have some issues with references, but we won't worry about that. Although our sensor's being measured with respect to a known potential, our electronic circuit doesn't know what that potential is. This is the half battery problem again. So we just need to link the two together. And this case is easy. We just tie the ground of the electrical circuit to the reference potential. Let me see if I can find it on this circuit on here. Can't see it on this part of the diagram. Yeah, maybe it's on the bigger one in a minute. But this is the circuit we end up with. We've got our differential amplifier, which turned out to be not the best solution, but worked okay in the circuit. We've got our analog multiplier with our one signal coming out and a choice of 8 signals coming in, and then we've got connections. These are just connections here where we connected our sensors to the input circuit. We put a capacitor on here just to put a little bit of filtering on, because they act as short circuits to ground, so there's nothing particularly clever about that. And then the interesting thing is here we've got a resistor string, which is basically just a potential divider, and this allowed us to present a known voltage to this input here, which we could then switch through here, which allowed us to test whether or not the multiplexer and the amplifier were working correctly remotely. Because if we can read the right voltage on when we switch to this point, we've got some built-in test, and then we know that everything's working okay. And if the signals coming into these other ones are a bit dodgy, that means the sensors are broken, not that the electronics are broken. And always have an LED in the circuit just to allow us to see it's working properly, and then some power supply stuff. And that's the that's the full system, really. So that was our basic electronics. We had to replace this in the end with a normal op amp, just to get us a range of operation. So we sacrificed common mode performance for normal amplifier performance, but that was good enough. We had to do it in the field as well, so we didn't have time to mess about with it when we got our circuit board. And the nice thing about this is it's low enough power to be powered from an I/O pin of a digital system, so we can turn it on and off just by changing the level of an output pin on a microcontroller, which allows it to be very low power when it goes to sleep. Some other stuff there, built-in test. We don't talk about the shielding at the moment. And the the board worked fine. We connected it to an Arduino, which had a built-in 10-bit ADC for our investigations, and then we tried it out in the field in Australia. Well, we didn't. We tried it in the lab first to make sure it worked properly. So we had an experiment with a drain pipe full of soil. We plugged in our sensors, so we had our 8 sensors plugged into here. Here's our reference electrode, and we poured salty water in the top here, and we watched it move through the column with our sensors. Each sensor would start to react as the salt started to move down, and we did a prediction of what it should be like and a measurement, and it all matched up really nicely. So we got a good idea that the sensor was working, was detecting chloride, detecting the right amount, was nicely calibrated and work. And then we went out to a field. Well, we went to this box, which was actually a box in Australia in a greenhouse, and did some experiments here by filling up a tub full of sandy soil, pouring putting salt into the solution, pouring water into it, drilling some holes in the bottom to allow it to drain out, and left it for 2 weeks. And took measurements, and these are 24-hour periods, so we can start to see the days involved here, and took lots of measurements. And these are the responses of the sensors, which are buried in the soil here, going along. And the red trace is interesting because that's one of the sensors, which you can't quite see, it's over here somewhere, but it's buried at the bottom of the tray, and these other ones are only about a couple of centimeters under the surface. So these are looking at the surface salt or just subsurface salt, and there was another one looking at the deep salt. And you can see over a period of time, this is when the battery went flat, we had to replace the batteries, things were fairly constant, and then the ones near the surface are starting to really respond. Their concentrations are really going up in terms of measuring the salt, and the red one really isn't. And this was generating some interesting questions at that point then, and all the hydrologists got really excited about this because this is the first time they'd been able to see what was going on here. So it says we got a diurnal variation in salt concentration, but in the last few days, as it dried out, it became very marked. And what you started to see eventually, when you get to this period here, where the salt is really getting very highly concentrated in the daytime, is you start to see salt crystallizing on the surface, because all the water's been driven away. Basically, this is drying out. But deep down, it's still quite moist, so you can still see what's going on. But the interesting point, I suppose, of all this is at night time, the readings go back to what they were in the daytime, and no one quite knew exactly what was causing this. They think it's a salt gradient between the deep stuff and the surface where it all organises itself, or it might be condensation at night coming in and redissolving the salt. But this is something that they go away and get excited about. And there's a zoom in of it, so you can see the deep sensor showing not much variation compared with the other ones, which are really going mad for it. So you might not be interested in exactly why that's going on, but it certainly got the hydrologists excited about what was going on. So this is trying to solve some problems or generate some information that allows people to then plan the use of land and where you put crops, and at least give information to the fact that if you have too much salt in the soil in the wrong places, it can cause the crops to die out. A lot of this is caused by digging up hedgerows and digging up trees, as it turns out. So this is arguments for not, or evidence to support the argument for not digging up the trees in the forest and having too much grassland. Anyway, I find that quite interesting. We're probably more interested in electronics in this course though. So it's probably worth looking at these differential amplifiers in a little bit more detail, given that we've seen there might be issues with common mode and getting the system right. So the use of single supply amplifiers in bridge systems. People want to use single supply amplifiers because we normally operate on a single supply. You've normally got a battery or a couple of batteries, and it's usually referenced to 0 and then the other end at 3 volts or 4.2 volts or whatever you want. So op amps these days want to operate in single supply systems, so it's important to understand about those. Right. In a bridge situation like this, we then would want to operate the bridge on a single supply as well. So we've got a 5 volt supply here, 0 volts here. Ideally we would want 5 volts here and 0 volts here to simplify the power supply arrangement for our measuring system. So it's obviously tempting to go for an instrumentation amplifier because this bridge is a differential system. Problem is though that if the bridge is in balance, then the output is 0. There'd be no voltage between this point and this point because the current through here is equal, so the voltage between these 2 points is going to be 0. So at that point that's equal to our negative supply value, so that becomes a bit of a problem for us. If we were operating on a single supply, a split supply, so if this was at 5 volts and this was at minus 5 volts, having 0 in the middle is brilliant and that's not a problem at all. But operating on 5 volts and 0 and having 0 as your input is a problem, as we've got a hint of. So if only we could amplify signals that are close to the 0 rail. It's tempting then to go for a rail-to-rail instrumentation amplifier, such as the one we previously saw, or for the sake of argument, this new one, the IN122. So again, we can look at the data sheet, give us a bit of an idea. This one's labelled as a micropower amplifier, so we'd expect it to be a lower power than the last one. And the quiescent current this time is 60 microamps. The last one was 550 microamps, so that's good. But you get a trade-off somewhere else. That trade-off is usually in bandwidth. So we'd have to, if we're interested in bandwidth, we'd have to have a look at that. All kinds of interesting stuff that we understand a little bit about now, and all kinds of stuff in there. So we might consider naively wiring it up like this. We've got a 5 volt, a 0, 5 and a 0, differential across here. The difference here is likely to be 0 if this is in balance, but we know this thing can go down to 0. The bridge is in balance, the differential input is 0. Yeah. So we're asking the amplifier to amplify 0. This should give us an output of 0, i.e. the same as the 0 supply rail. So, nothing in, nothing out sort of thing. So we know about common range mode, as we know that could be tricky. It says the common mode input range goes to 100 millivolts below the negative supply rail, which is great. But we should also be aware that this might have an impact on our output voltage, as we saw a few minutes ago. So we should ask ourselves, what is the common mode voltage in this system? Assuming a symmetric bridge, the common mode voltage is actually 2.5 volts here and 2.5 volts here, so the common mode is 2.5 volts, but the differential signal we're interested in amplifying is 0 because it's the difference between the two. So we're on a 2.5 volt common mode, which sounds good, and we need to then dig into the data sheet to find the common mode system and see what's going on in there. And we, on a 5 volt supply system, which is this bit here, we're operating in this shaded region, and there's this interesting hat to the top of the graph. So this is input common mode voltage and output voltage, so it's the other graph turned on its side in many ways. So we just have to work out where we are in here. So our common mode voltage we said was 2.5 volts, which is here, and we'd be operating at 0. So in fact we're okay. We're starting to get a little bit of output range, or output voltage is allowed here. So that's all okay. So we get an idea of what's going on there. I was zoomed in a bit more detail. I've forgotten we'd done that. Right, so we're okay on this amplifier, is what this is telling us, and as part of your homework you should be looking at this and trying to understand in some detail what this graph is actually telling you, so you get a good handle on the limitations going forward here. But a quick look on the output voltage range seems to show operation all the way down to 0. But a closer look shows the dotted line doesn't quite stretch as far as 0. This implies that 0 in might not give us 0 out, i.e. it may not be truly rail to rail. And if you look at the specs in some more detail, you get this point. So you can see here output voltage positive and negative, and it tells you that it can go to the positive voltage less 0.1 of a volt and a negative voltage plus 0.15 volts. So it's not quite rail to rail. It gets to within about a tenth of a volt of the rail. So in summary then, this shows us that we only get to within 100 millivolts or so of the supply rail, the input. If the expected output is less than 100 millivolts, then we won't see it because the output can't move to within 100 millivolts of the rail. So 0 volts in will give you something close to 0 out, but it will be 100 millivolts irrespective of whatever it is, and the input has to be bigger than a certain value before this output signal starts to move at all. But chip designers have thought of this. They give us a reference input on the chip. There's another pin that we haven't looked at yet. This allows us to add an offset voltage to move the output away from the rail, so we can offset the output a little bit. We've still got to generate this reference, which adds a bit more complexity, but maybe we can do it like this, and this maybe helps a little bit in describing it. So here's our bridge operating on 0 to 5 volts. So when it's in balance, there's 0 in. So we would expect to get 0 out, but we can't get 0 out when we're operating on a 0 to 5 volt supply, because this output only works down to 100 millivolts close to here. So anything between 0 to 100 millivolts input will only allow us to have 100 millivolts out fixed. So 0 in here gives you 100 millivolts out here, because that's as close as it can get to 0. However, if we input something into this ref input and we offset it by 100 millivolts or more, then this output moves up by 100 millivolts, and then it's got 100 millivolts of leg room to go down, so it can then amplify things that are smaller than that. It just gives it a bit more room to maneuver. But we've got to generate something, and 100 millivolts is a bit close to the limit, so maybe you want 200 to 300 millivolts of offset in here. So we need to be able to generate 200 to 300 millivolts of offset. So we have to think of a way of doing that. So here's what's known as a reference. So it's a 3-terminal chip, looks like a transistor, and all it does is give you out a fixed voltage reference, very accurate, set by a band gap diode. And 1.25 volts is a very common output voltage for these things. So this will always give you 1.25 volts irrespective of what this voltage is here, unless this gets really low. So you get a fixed volt reference, a fixed 1.25 volt reference from here to 0. That's too big, so we put it through a potential divider so we can get a small voltage here. We would then put it through a buffer to make sure there's no impedance effects, because we're interested in keeping this voltage absolutely fixed, and we don't know what loading effects this pin would have, so we buffer it, and then we present the divided version of this voltage here to the reference pin, which then offsets the output of our amplifier. Now we put a buffer in here, so we have to make sure that this buffer is a rail to rail buffer, because we're putting in a low voltage 200 to 300 millivolts in here, and we want this to be an exact copy of that. So the output needs to be able to cope with supplies within or outputs within 200 to 300 millivolts of the supply rail. So you can see the devil is in the detail of these. There are loads of op-amps. I've chosen an MCP 6241 in this case, which is just a standard microchip modern op-amp. And this allows us to offset the voltage here. So 0 in now gives us 300 millivolts out. Okay, but the advantage of this is that if we go negative a little bit here now, this will go negative. It's allowed to go negative as far as 100 millivolts at least. We can make this reference as big as we like. We can move it up to 2.5 volts if we want to do, and that will give us an equal plus and minus output on here. But if you just want a single-ended system, so this is say a weighing bridge that only goes positive because it goes from 0 up, we can't weigh negative masses, then making this as low as possible makes sense, because this allows this signal to go as far as it can in this supply. So it gives us a very good dynamic range. If this bridge can go negative, then you might want this reference to be halfway between the supply rails at 2.5, so the output can go up and down as this bridge goes up and down. And in this case, we're only expecting the bridge to go up, so we just put this at the bottom end of the range that we're interested in. I hope that makes sense. It should be obvious when you read about this later in your own time. Right, so that's the limits of amplifiers and things like that. How can we sort of use these things, and what else what other block diagrams can we use? So dynamically adjustable gain is always a useful thing. How do we change the gain of an amplifier electronically without having to go and change resistors? So the direct approach is to just do exactly that and just change the resistors. And we do it in this system called a digital potentiometer. So you can actually build these if you want to. You can just put a resistor chain down here, so you've got a multi-level potential divider, tap off the different voltages and put them through an analog multiplexer. As we saw earlier, we can control that digitally, and it selects one of these voltages here to come out of here. So that's that's effectively potential divider gain control. Very straightforward, very basic, and a bit limited in what it can do. However, people have taken this to another level now, and you can buy integrated systems. So you can buy, and these are particularly good for digitally controlling volume of amplifiers, for headphone amplifiers and things like that. You can buy chips that have got maybe 128, 256, 512 different precision resistors in a chain inside here, and a built-in analog multiplexer, so that you can just select a value of resistance digitally in these chips, and it just looks like a resistor to you that you can control digitally. And so you can use that as the gain controlling resistor in an op-amp, or across here really, from here to here. And it allows you to make a digital potentiometer, which is dead easy to control as long as you've got a microprocessor in your circuit. And there are loads and loads of these to choose from now. Some of them are matched to the ear's response, some are logarithmic, some are linear. The problem that you do get with them, they don't advertise, is that although they are mainly a bunch of resistors, there's always going to be some stray capacitance associated with these resistors, some parasitic, and then you've got an RC time constant, and that leads to a frequency response. So these are not great for high frequency systems. So they've been designed to be good at audio, so anything up to about 20, 30, 40 kilohertz they'll be okay for. But after that you have to be careful, because their signals will roll off with frequency, and it doesn't tell you that in the datasheet. You have to find that out the hard way. If you want to make a variable resistance, you can. There's an alternative technique. I just put this in for interest, really. For those of you who are interested in analysing interesting circuits, it looks like a complicated circuit, but you can apply it with nodal analysis. You can analyse it with nodal analysis and basic circuit basic circuit techniques, and you can show that if you implemented this and controlled the value of this digital to analog converter digitally, you can make a digitally controlled resistor, and the resistance is measured between this point and this point. So this whole block looks like a big variable resistor across here. Okay, it's complicated, but it's an interesting technique, and there's some basic analysis giving you the headlines here, which you can follow through if you want to. And so the circuit operates as a voltage controlled current source, which is the definition of resistance in many ways. And it's the sort of thing that you can use in an integrated system, and it says for use as a basic functional block in the design of a biquad filter. So you might not know what a biquad filter is, but we'll be doing that in a couple of weeks' time. So we'll understand the basics of a biquad filter, which is a very versatile filter block, and then you can start to say, well, actually some of the resistors in there that need to be controllable I could replace with something like this, which is quite accurate for resistant, or one of the digital resistors that we just looked at on the previous slide. And I think on the notes pages, the old notes pages that's linked to through Blackboard, there is a worked example of how to analyse this in with some detail. So if you're interested in working out why these equations apply to this rather complicated circuit, and how circuit analysis can be applied to that, that's there, I think, or if it isn't, I'll put it up there shortly. So that's sort of digital control. That leads us quite nicely onto analog gain control. So analog gain control is, as it says there, effectively a multiplication function, and we'll try and expand on that a little bit. So analog multipliers, which you may have looked at in the second year, which just multiply two analog voltages together, can be used. And this is really nice, takes us right back to this long tail pair again, so you can start to see that this long tail pair, which is the input of every op amp that exists, can be used as a multiplier, and it becomes it's a really useful circuit to understand. Again, you can get these integrated, and AD534 is a typical analog multiplier that can run to quite high frequencies as well. And the trick to this is remembering that the gain of a transistor is defined by GM, its transconductance. So here's the long tail pair, here's a small signal analysis of the long tail pair, how you can draw it. And look, the gain of the transistor is controlled by GM. GM multiplied by the input voltage gives you the current through the device. And remember, GM is defined by the value of the bias current flowing through it. If you change the value of the bias current, which is defined by this thing down here normally, this current source here, if you change the value of this current source, you change the value of GM, which changes the overall amplification factor of the amplifier. And that's the trick to it. So it boils down to, how do we make a programmable current source in here, and that would change the gain of this amplifier. And that's just telling us in more detail that GM is defined by the bias current and a whole bunch of constants, for want of a better word. So that's what happens. So we can take our long tail pair, and we're interested in this bit down here, and we can replace this with what you might recognize now as a current mirror. So the current through this transistor must be the same as the current through this transistor, because their VBEs, the voltage between here and here, is identical, because that's the way they're connected. So whatever current is programmed into here, the base current, from this voltage here, becomes the current that goes through this transistor here. It's mirrored. Whatever you put into this transistor is mirrored in this transistor. So by varying this voltage here, we vary the current going in. By varying the current going in here, we vary the current through here, and therefore we must vary the current through here. If we vary the current through here, bias currents through these two transistors will be, the split of that will be varied, and the gain, the GM of this transistor, will be varied, and therefore the gain of the system as a whole will be changed. And that's what we're getting to with that. And you can sort of see it in operation here, simple simulation. We've got a high frequency signal being a differential signal coming into these two terminals here, which is then being amplified by whatever the gain of the system is. So we would expect to see a constant amplitude envelope here, but because we're varying the tail current by a slow moving voltage here, we change the current through here. A slow moving current change here changes the bias, changes the gain. We end up with a varying gain, which is where you see, so here's the low gain, and here's the high gain. Here's low gain and high gain. So we've actually made a modulator. But the reality is, all we've done is change the gain of the amplifier by changing this here. So we keep this fixed, we get a fixed gain. Change it by a little bit, we get another fixed gain, but changed by a little bit. Okay, so this officially is just a 2-quadrant multiplier, because it can't go negative, or this voltage always has to go positive. But for a lot of gain control problems, that's not really a problem. For completeness, a 4-quadrant multiplier allows both inputs to be positive or negative, so this one can go negative as well. But in this case, this is just a 2-quadrant one, and that's good enough. So I think at that point is a good point to stop, because we're starting to get into some very elegant analog design ideas, which have some relevance going forward still. So I'll stop at that point and pick that up whenever the next lecture is, next couple of days or so. So I hope you found that interesting, and I'll see you in probably tomorrow, isn't it? Whenever it is. Okay. Goodbye.